Hey class, this is Juan Ramirez with EE 2715, Circuits 2 Transients. And today we'll cover Chapter 8.6, that is step response of a parallel RLC circuit, which is within the second order circuits chapter of the book, Chapter 8. So Section 8.5 was on step response of a series RLC circuit. That step response we modeled with the input being a step voltage. For a parallel RLC circuit, we model it with a step current. That's sort of what you see in practice most of the time. And you could also kind of recall that from Thevenin and Norton equivalent circuits. Thevenin looks at a series impedance and a source, and Norton looks at a parallel impedance and a current source. So parallel we usually apply to current sources and series to voltage sources. So now let's start off with redrawing the parallel RLC circuit, but with a step input. Like always, I'll actually write out a parallel RLC circuit with a step input. Okay, so we have our current source. The switch is in parallel with the current source, not in series. Why is that? Well, that's because before that, before the transition, the switch is closed, meaning all the current of the current source goes through a short circuit. None of it actually goes through the resistor, inductor, or capacitor. Because it's a short circuit, the voltage at the current source is actually zero. A current source could have zero voltage and be supplying current, even though that sounds funny. But if you think about it from the voltage source perspective, a voltage source could have voltage and be applying voltage to an open circuit and have zero current. So the analogy kind of works in both regards. Then the switch opens, and then all that current will get dumped into or sourced into the resistor, inductor, and capacitor. Okay, so what do we know? We know that the voltage of the whole circuit we call V of T. Everything's in parallel, so they'll share that. You have R, L, and C, and you're going to have a voltage across your capacitor, Vc of T, and a current through your inductor, IL of T. And by inspection, you could tell that V of T is equal to Vc of T, right? So similar to what we did in section 8.4, which was the source-free parallel RLC circuit, we're going to do KCL at that only node, assuming the bottom node is the reference node. And now KCL will have one current going into the node, which is IS, and the rest of the currents are leaving the node, which are the voltage, V of T, over R, plus I, which is the inductor current, plus the capacitor current, which is C dV dt. And then we say, but V, which is equal to VL, the inductor voltage, is equal to L di dt. V is equal to the voltage across all those components, so it's equal to the inductor voltage, capacitor voltage, and resistor voltage. since those are all in parallel. So if we replace all of our V's with di L di dt and do some simplification, we end up with d squared I dt squared plus 1 over RC di dt plus 1 over LC I equal to IS over LC. Again, it pretty much has the same type of response as a source-free parallel RLC circuit. Except now it also has that source current IS divided by LC on the right. Okay, so what does that actually do to our solution of current? And again, notice this time we're solving for inductor current for the parallel RLC, not capacitor voltage like we did in section 8.4. Nonetheless, they have the same response, which is interesting. And the math shows us why. So again, the solution has two components. We spoke about those components for the step response of the series RLC. The two are the transient and the steady state. And the transient includes the initial conditions as well. So based on however you want to think about it, you could say it has three components, which is kind of what we would say for first order circuits. Initial condition, so what happened way before the switch closed or the transition happened. Transient, what's happening during that transition and while things settle. And then steady state, which is what happens way after that transition. And what do voltages and currents look like at that point. Okay, so the solution is going to be I of t equal to IT of t plus ISS of t. So transient current response plus steady state current response. Okay, and for the circuit above, or again, I guess I'm going to come over here and say steady state response is going to be simply the final value. And then I'm going to say in the circuit above, right after that transition, or sorry, not right after, if you look at it a long time after, the inductor looks like a short circuit, so all of that source current will flow through that inductor. Therefore, the steady state current will be equal to IS. Okay, now let's take a look at the solution for the different types of response. Okay, so again, we have the three different response types. One is overdamped. That's when your damping factor is greater than your natural frequency. And this is actually the solution for this given circuit, the really basic step response of a parallel RLC circuit. So instead of that capital IS, it would be the steady state value plus the transient value. Okay, and then critically damped. And finally, underdamped. Okay, so that's the solution for the different types of response for the circuit that we just analyzed. And again, the general solution will be, x of t, which could be voltage, could be current, will be equal to the transient response, so x t of t, plus the steady state response, so x ss of t. All right, so we've kind of covered every type of value, right? So that's capacitor voltage in a series RLC circuit, inductor current in a series RLC circuit, capacitor voltage and inductor current for parallel RLC circuits. And once you have those values, you may be looking for a different value. You may be looking for resistor current or resistor voltage or capacitor current or inductor voltage, or maybe current coming out of the source, out of the voltage source, or voltage across the current source. You could be looking for any of those other things. At that point, as long as you have that capacitor voltage and or inductor current, you could do some basic circuit analysis to find the remaining ones. Okay, so we don't use this actual step-by-step method to find resistor voltage or resistor current directly. We kind of do it indirectly by first finding capacitor voltage and or inductor current, and then doing some circuit analysis. That circuit analysis we do is after the transition. So, we assume time has gone by, and so actually we would look at the circuit right after the transition, because we want to actually consider the inductor for an inductor, capacitor for a capacitor, not a short circuit for the inductor or open circuit for the capacitor. We'll do a couple of examples in the next section called general second order circuits. In that section, we'll look at, hey, what if we want resistor voltage? What if we want resistor current? Some of those different values, and we'll see how we actually do what I just mentioned. Okay, so for this one, let's do one example. Okay, so example 1. We want to find I of t. And the example looks like this. We haven't used a lot of actual step functions as opposed to switches in the examples for this chapter. So I'll try to do that a little bit more, but I think you guys kind of get the difference. A very subtle difference. And I might as well remind you what that is. With a voltage source and a switch in series, when the switch closes, you apply a voltage, but when it's open, it's actually looking like an open circuit. That part of the circuit is. Whereas with a step input for a voltage, when the step input is high, then, sorry, I'm terrible at multitasking. When the step input is high, you apply the voltage. When it's low, when let's say you have 0 volts, that's replaced with a short circuit, not an open circuit. Okay, and that's because 0 volts is represented with a short. And then if we're thinking about current sources, a current source with a switch in parallel with it, that current source will be, when the switch is open, you have regular current going through. When the switch is closed, that current source looks like a short circuit. Whereas when you have a step input for a current source, when it's high, it's supplying current normally. When it's low at 0 amps is represented by an open circuit. So just make sure you remember those 4 different scenarios. Okay. Oh, we need resistance. All right. So the first step is we're usually not big fans of having, especially for these types of circuits where you want to simplify the circuit as much as possible. We're typically not big fans of a voltage source and a current source. It's also not very clear what the series or parallel resistance looks like there. So the very first step here is going to be to redraw the circuit. I'm going to convert the Thevenin voltage source because it has a series resistance with it. So I'm going to convert that Thevenin voltage source to a Norton current source. Okay, so the Thevenin voltage is 45. Thevenin resistance is 10 ohms. And by source transformation, we know Norton current will be Thevenin voltage over Thevenin resistance. That's 45 volts over 10 ohms. Gives you 4.5 amps. Norton resistance is simply equal to Thevenin resistance equal to 10 ohms. Okay, how does it look when we redraw it? Remember that Norton resistance is in parallel, not in series. And I apologize, my penmanship with the OneNote is not amazing. Okay. Everything else kind of looks the same. But at that point, what we do is recall our first step is let's first do sort of a straightforward step, which is this a series RLC or a parallel RLC? First thing I'm going to do is I'm going to say, well, this is clearly a parallel RLC. The inductor and the capacitor are in parallel with each other. Resistor as well, but we have 2 resistors. So we'll have to find the equivalent resistance, but I do know that this is a parallel RLC circuit. That said, there are some tougher examples and problems in the book where you could have a circuit that has parallel and series resistors connected to one of the capacitors or the inductors. So those are more complicated. We may look at that in chapter 8.7. But for now, we focus on one or the other, series or parallel. Now, we're going to look at damping factor. We need a Thevenin resistance for that, or rather just an equivalent resistance. So what is that equivalent resistance? that is after the switch or the transition. And we turn off all the sources. So after the transition, you have the 4.5 amp source and the 9 amp source, the step input, but you want to turn those bad boys off because that's what we do to find equivalent resistance. And when you do that, and you also disregard the capacitor and the inductor, so you pretty much disregard everything except the resistors and keeping the connections the same. And when you do that, you make the current source an open circuit, and I'll just kind of draw it to make it clear. I still draw the capacitors, but we kind of disregard those. Okay, and you have 10 ohms and you have 40 ohms. Those are the only two resistances. They are clearly in parallel with each other. Therefore, the equivalent resistance will be 10 ohms in parallel with the 40 ohms. Right? And we say they're in parallel because of what the inductor and capacitor look like right next to them. They are in parallel as well. So we combine those resistors in parallel. Because if we completely disregard the capacitor, the inductor, and pretend they don't exist, then you could also kind of say, well, they're in series because the current sources are now represented with an open circuit. So be careful with that. You have to also consider the capacitor and the inductor and how they look in that circuit. That's a little bit of a tricky one. And it's not as tricky once you have said, hey, I know this is a parallel RLC circuit, or hey, I know this is a series RLC circuit. This is parallel. We know those resistors are in parallel. Okay, let's see what we got next. Alpha, damping factor. Because it's a parallel RLC, we do 1 over 2 times the equivalent resistance, which we never actually wrote down. That comes out to 8 ohms. So 1 over 2 times R times C, 10 millifarad. That comes out to 6.25. Natural frequency, 1 over square root of LC. Okay, and we get 5 radians per second. Damping factor is greater than natural frequency, so once again we have an overdamped system. Overdamped systems are kind of nice, and critically damped too. I think the underdamped are more fun to look at, but they require a little bit more work because they have the cosine and the sine multiplied by the exponential, so the initial conditions become not so fun. Okay, let's look at the characteristic roots. That's going to be negative alpha plus square root of alpha squared minus omega squared, omega not squared. So we kind of have done a few of these examples now, so I won't write out the equation. And we get negative 2.5 here. And negative 10 for the second characteristic root. And finally, we start looking at, I guess not finally, but next we start looking at finding initial conditions. So we are looking for inductor current, and therefore the initial condition will be that inductor current right after the transition and the rate of change of that inductor current. Right after the transition, like always, we'll also look at capacitor voltage right after the transition because that usually helps us with that dI/dt. Okay, now let's look at the circuit way before the transition. So that's a steady state situation. I'm going to represent that resistor with 8 ohms, which is that equivalent resistance of both of those puppies in parallel. Capacitor represented with an open circuit because this is a steady state condition. And inductor represented with a short circuit, again steady state condition. By inspection, that inductor current will be, that'll take all of the current, right? Whenever you have a short in parallel with a resistance, the short takes all the current because a short circuit by definition has no voltage across it. And if there's no voltage across it, that means there's no voltage across the resistor because they're in parallel and they share or have the same voltage. No voltage across the resistor means no current through it according to Ohm's law. So that's why by inspection, all the current will flow through that short. Again, by inspection, because of that same reason, it's a short, so there's no voltage on it. Okay, now let's take a look at the circuit right after the transition. We kind of analyzed it already that way before, but we'll go a little deeper now. Notice, let's go up real quick. Notice when we look at the circuit, right after the transition, those current sources are in parallel with one another. The 4.5 amp and the 9 amp, after the transition, which is when the 9 amp is there. They're in parallel, and I think it's a little bit more intuitive to think that voltage sources in series add up, but also know that current sources in parallel add up. Okay, so I could draw this as one current source equal to 4.5 plus 9 amps because they're in parallel. If they're in series, they don't add up that way. So kind of opposite to voltage sources. Voltage sources in parallel don't add up and are actually quite dangerous. Voltage sources in series do add up. Fun fact, I'll be quick. Voltage sources in parallel are pretty much what you're doing when you are jump starting a car. So you're taking the battery of a car that is on and has the battery healthy and it's at its nominal voltage, maybe it's like 13.2 volts, and then you have somebody else's car or your car that won't turn on because the battery is at a very low state. Its voltage is much lower. Maybe it's 11.2 volts or something like that. So maybe there's a 2 volt difference between the healthy battery and the battery that's dead. And then you wire those bad boys in parallel. Don't do it in series because that'll be bad. But you wire them in parallel, so red wire to red wire, black to black. And then the healthy battery will supply current to the not healthy battery. Well, what limits the current? If there's 2 whole volts of difference between it, we know KVL is a thing, but what limits the current is actually the resistance of those jumper cables, which is pretty low, so it'll be a relatively high current being sent from the healthy battery to the not healthy battery. And that's why you do it while the car with the healthy battery is on and running, so that the alternator could continue to charge up that battery that's supplying all the current. And then you keep things connected when you try to turn on the car with the battery that has a dead battery. Anyway, okay, sorry, we're going back to it. So 8 ohms, because that's the equivalent resistance. Then we have that capacitor. We know the voltage across it is the same as the voltage across the capacitor before, because it doesn't change instantaneously. And we know the current through that inductor is the same as the current before, because that doesn't change instantaneously. And then we care about the IDT right after the transition, which at this point you should be very familiar, is equal to the inductor voltage divided by the inductance. Well, the inductor voltage is in parallel with that capacitor, or the inductor is in parallel with the capacitor, hence the inductor voltage is equal to the capacitor voltage. And that capacitor voltage we just found to be 0 volts. And so the capacitor voltage divided by the inductance is equal to 0 amps per second. Sorry. Okay. The only I'd say big difference when we have a step input to a parallel RLC circuit is that now we also have to look for the we have to find the steady state value. We have to look for the final value of the inductor current. Okay. So now we're going to analyze the circuit a long time after the transition. Again, it still has that 13.5 amps. Still has the 8 ohms. But now we're analyzing the capacitor as an open and inductor as a short. And we said because of that short, all the current will flow through it, and that's 13.5 amps. It's a funny looking 13.5. Okay. And if we wanted to look for the final capacitor voltage, we could. It's equal to 0 because it's in parallel with the short. Okay, now we're going to find our inductor current. It was overdamped. I'll just write that out. And because it was overdamped, the transient will kind of follow that response, which is A1 e to the S1t plus A2 e to the S2t, and then you have to add the final value of the inductor. So what does that look like? If we plug in the values we know the characteristic roots, we know the final value. Okay, now let's plug in our two initial conditions. We said the initial inductor current was 4.5 amps. Okay, so A1 e to the 0 plus A2 e to the 0 plus 13.5 is equal to 4.5. So that means A1 plus A2, if we subtract the 13.5 on both sides, will give us -9. So our first equation, If you recall, for overdamped, the initial condition for current, inductor current, and the initial condition for the rate of change of the inductor current will give us two equations in terms of A1 and A2, and we have to do system of equations to solve. So what is the IDT? The IDT is negative 2.5 A1 e to the negative 2.5 minus t A2 e to the negative 10t, and then the final value derivative of that is 0, so isn't included there. Initial condition, plug in 0 for values of t, and set it equal to that final value, which was 13.5. Or sorry, not final value, but rather what the dIdt was equal to right after the transition, which was 0, if we look back. dIdt right after the transition was equal to 0. Sorry, there's a delay. Okay, there it is, sort of at the top. The IDT after transition equal to 0. Now let's solve for A1 and 2. And that gives us the second equation. So if we take the first one and kind of write it in terms of one or the other, let's say A1 is equal to, what is it? Negative A2 minus 9. Okay, and then A2, or if you plug in 1 into 2, we can rewrite the second equation as negative 2.5 negative A2 minus 9 minus 10 A2 equal to 0. Right? And so what do we get here? We get positive 2.5 A2. And then plus, again, 9 times 2.5, which is what? 22.5? Minus 10 A2 equal to 0. Okay, so that'll give us negative 7.5 A2 equal to negative 22.5. I can't quite do that one in my head, so maybe I could have. Okay, it's equal to 3. Okay, now we can plug that into our first equation, which said A1 is equal to negative A2 minus 9. So that's equal to negative 3 minus 9 equal to negative 12. Let's plug that into our original equation, and we'll be good to go. Negative 12e to the negative 2.5t plus 3e to the negative 10t plus 13.5. And that's in amps after time 0. Okay, that's our answer. So again, you probably see that there's a lot of similarities between each of these sections. I think once you have down the source-free, series, and parallel RLC circuits, adding the step response, or the step input rather, doesn't change the response too much or the work you'd have to do to analyze it. Thank you very much for watching. Please check out the book to review the concepts and look at some more examples.